This is the video for problem 2.25 of Engineering 623. This problem says the following. Consider the quarter wave matching transformer circuit shown in the accompanying figure. Derive expressions for V plus and V minus, the respective amplitudes of the forward and reverse traveling waves on the quarter wave line section in terms of VI, the incident voltage amplitude. So let's see how this goes. Some of this problem is a little tedious algebraically, and we won't worry too much about those details, but the first part is definitely important. So in this case, we have gamma at the load is equal to, as usual, RL minus, now remember this is the characteristic impedance of the line, square root of Z naught RL. So we have RL minus the characteristic impedance over RL plus the characteristic impedance, and that is gamma at 0. Now for gamma at the input of the line, since the line is a quarter wavelength in length, then that's gamma of negative lambda over 4, and using our standard formula, that's equal to gamma of 0 times e to the j2 beta times minus lambda over 4. Well, this exponent here just becomes minus j pi, and e to the minus j pi is negative 1. So gamma of negative lambda over 4, that is the input reflection coefficient, or the reflection coefficient at the input, is just negative of the reflection coefficient at the load. Now, Zn is, again, since the length of the line is minus lambda over 4, that's Z of minus lambda over 4. And we know that the formula for calculating Z at any point along the line is the characteristic impedance, which again is square root of ZORL. Is the characteristic impedance times 1 plus gamma at that point divided by 1 minus gamma at that point. So since we want Z at minus lambda over 4, that becomes square root of ZORL times 1 plus gamma of negative lambda over 4 divided by 1 minus gamma of negative lambda over 4. And since we have found out that gamma of negative lambda over 4 is minus gamma of 0, and gamma of 0 is here in this first line, that all becomes this. The Zn is equal to, here's the square root of ZORL, then here we have 1 minus gamma of 0 over 1 plus gamma of 0. And so we do a little bit of algebra here, and we get this very interesting result that Zn is equal to Z naught. So this is matched, and that's what we want. That was the point of using the quarter wave transformer, was to get matching. So that means that there will be no reflection there, and the voltage across the input of the quarter wave transformer is simply VI. And that's what we have here. V at the input of the quarter wave transformer, V of negative lambda over 4 is VI. So VI is equal to V of negative lambda over 4, and which is V plus times e to the minus j beta times negative lambda over 4 plus V minus e to the positive j beta times minus lambda over 4. And then as usual, we can factor out the V plus e to the minus j beta times Z, and then we're left with 1 plus V minus over V plus e to the j2 beta Z, which of course is 1 plus gamma of Z. And so we then, when we evaluate this at Z equals minus lambda over 4, then we get VI on the left-hand side. So that's where this equation comes from. And remember that gamma of negative lambda over 4 is minus gamma of 0, so that's how we make this switch from here to here. And then substituting for gamma of 0, we have this. Here, e to the j beta lambda over 4 is the same as ej2 pi, which is just j. And so we get that Vi is equal to j times V plus times this. And therefore, doing just a little more algebra, we get this expression for v plus, which is one of the things requested for this problem. And this is a nice, simple expression. However, to get v minus, remember that v minus is gamma of 0 times v plus, and so substituting what we had previously for gamma of 0, this is our gamma of 0, RL minus square root of 0 or RL over RL plus square root of 0 RL, or Z naught RL. And then we have this formula for V plus, which is minus J times VI over 2 times the quantity 1 plus square root of RL over Z naught. Well, this gets a little tedious algebraically, and I'm sure that different people might terminate this calculation at different points. I worked down to this expression right here. I don't believe that there are any algebraic errors, although there certainly could be. But the main thing I would say for this problem is it's important that you see that the input impedance is Z naught. That's very important. And I think the formula for V plus is simple. So it's important that you be able to get this equation. But for V minus, you should understand that this first equation is valid. And then if you want to try to verify that this is correct, that'd be great. But don't worry too much. And if anybody catches an error, definitely let me know. So that concludes the discussion of problem 2.25. And in problem 2.30, which will be the last one we'll do for this problem set, again, we'll see that at some point in the problem, it becomes rather tedious algebraically. But we'll discuss that in the video for problem 2.30.